So to finally try to wrap back to the mystery that I had started you all off with, uh, is all the derivations to the basic elements of resistor, inductor and capacitor really help you solve the mystery that you saw, right? And I would say that perhaps not, right? But I have identified a key missing element that you must have asked yourselves, right? In the chronology that you were taught electromagnetics in your high school, you were probably doing all these derivations for inductors and capacitors before you were actually uh, told about this changing electric fields causing magnetic fields, right? So, perhaps at the end of your class 12, you can probably ask yourself, right, that why is it, going back to these derivations, that the changing electric fields causing magnetic fields was not introduced into these derivations, and does that actually change the way we look at these toy models for capacitors, inductors and resistors, right? But I do not want to leave you hanging anymore. What I will do is I will perhaps tell you the reason for the observation that we saw on the oscilloscope, right, because it is a precursor to what is to come next, right. So, although we talked a lot about what was happening within the capacitive plates or within the windings of an inductor or within the conductor of a resistive piece of wire, it is important to also notice that there are elements outside of what is considered the capacitor or the resistor or the inductor, right. So, remember back that the capacitor had two leads coming out, right, and these leads were sufficiently long leads compared to the capacitor plates themselves. So, the phenomenon you saw was from the fact that when there are currents and voltages that are fluctuating, right, the underlying fields that are responsible for what you actually see as voltages and currents are actually fluctuating with time, right. So, and these time rate of change of fields actually cause creations of new fields, right. So, a time rate of change of magnetic fields can cause electric fields, and time rate of change of electric fields can cause magnetic fields, right, which means to say that in any element that you may choose to make in real life, right. So, remember that this capacitor is just as the toy model dictates you to make a capacitor, which is to go take a pair of plates of conducting metal, and we need a separator here, and so we use a simple dielectric. So, if you were to break open the ceramic capacitor, you will find two plates with a dielectric spacer, and you might say that this is as close as it looks to the toy model for a capacitor, and it still seems to show this inductive behavior. So, what I am trying to really point at is the fact that time rate of change of electric fields causing magnetic fields is something that has been avoided in these derivations, and when you incorporate those, you notice that there can be significant amounts of values for both electric and magnetic fields in any given scenario for any given element, right. And it is usually the ratio of the energy that is stored in the magnetic fields to the ratio of the energy stored in the electric fields that dictates whether a particular component acts as a capacitor or as an inductor or a resistor, right. So, when you go with these toy models to actually making real world circuit elements, you understand that what happens inside these elements in reality are quite complex and not completely covered by the toy models that were shown to you, right, in high school, and that the real picture that goes behind these terminal currents and terminal voltages, the hero of the show, as you may call it, are the electric and magnetic fields, and that when they start changing with time can cause fields of the other kind, right. So, and when such mechanisms exist for fields to have an interplay between them, we notice that there can be both magnetic field energies and energies stored in the electric field, right, and the ratio of these energies can actually be manipulated by the rate at which you are willing to fluctuate these external voltages and currents, right. So, keep that in mind. So, what essentially was happening was there was some electric fields and magnetic fields in the regions between these leads of the capacitor, right, and the proportion of the energies in these fields tends to change with frequency, right. So, if you do not trust me, which a good engineer in his early stages of learning should, to not take anything that his instructor says for granted, you can actually notice that this behavior and the frequencies at which it kind of toggles from going to have a capacitive behavior to an inductive behavior can be manipulated by simply trimming these leads, right. So, that way you can say that the leads have something to do with the observed behavior, right. So, while I am not giving you an entire solution to the mystery as such, I am merely giving you pointers to say that toy models, when tried to when you try to realize them in practice, it is the true fields that you need to keep track of in whatever you are building, right, and these fields themselves may be acting in strange ways, right, and to uncover the ultimate impact on your circuit, it is important to always trace them back to fields, right. And this is also emphasizing the fact that whatever treatment of electromagnetism that we are doing in this course is perhaps trying to identify that there may be a delineation in frequencies, right, and we are particularly interested in the high frequency phenomena, right. So, this course goes over trying to understand the behavior of circuit elements through the study of fields to predict behaviors of the circuits at very high operating frequencies, right. So, you may say that, sir, we have been using the capacitor and inductor IV relationships successfully in many scenarios, right. So, in fact, in low frequency applications like power generation, where they deal with low frequency and high power, we continue to use these IV relationships and it seems to hold good, right. But it seems that when we go to very high frequency realms, that we start seeing some very odd behavior that requires some level of explanation. So, at this juncture, what I will say is, let us try to wrap up this unit with summarizing all the relations between fields that we know of from high school and distinguish them between the static and the dynamic case, and then we will say that these equations form the bedrock of any studies that you may want to do with these fields, right. So, the first of the statics equation is Gauss's law. So, this is a closed surface integral E dot dA is Q enclosed by epsilon 0, right. And we have the accompanying Gauss's law for magnetic fields, right. The other way that it is stated is also that there exist no monopoles, which means to say that if I were to take a bar magnet that has north and south, and if I were to cut it in the middle, I actually get two magnets with their own independent north and south. So, there exist no monopoles, and these poles come always in pairs, right, that have, and so the closed loop surface integral will always be 0. So, you can also you would have got the same kind of expression if charges also came in pairs, right. So, if you said that you could not separate a positive and a negative charge and that they always came in pairs, the Q enclosed will always be 0, right. So, then we have the line integrals, right. So, this might also be reminiscent of your Kirchhoff's voltage law, right. So, when I do not have time rate of change of magnetic flux, the static electric field E, when taken over a contour, will be 0, right. So, when we go around the loop in a circuit, we say that the sum of all voltages over the entire loop should be 0. It stems from this particular equation, right. And then the last one says that if I have a current carrying wire and if I have a contour wrapped around it, the line integral of B around that closed contour is equal to or proportional to the current carried in the wire. So, this is the static set of equations where all the time derivatives have been made to 0. The reason to explicitly write this down, although I am not a big fan of separating dynamics and statics, is that there are only one set of Maxwell's equations, and which is the dynamical equations. You can always turn off the time derivatives to 0 in the dynamical equations and get the static equations, but to explicitly write it down on the slide is to show that in the static case we actually see that there is no connection between electric and magnetic fields, right. So, the relationship of electric fields causing magnetic fields and magnetic fields causing electric fields is purely a dynamical phenomenon, right. If everything was static and not moving, these electric and magnetic fields look like independent entities of themselves, right. So, perhaps you can understand the reason why for many years scientists were thinking that electric and magnetic fields were two separate subjects, right. Unless we got into time dependent phenomena, we could not have uncovered this intricate relationship between E and B. So, the Maxwell's equations in its integral form is best written with the following set of 4 equations, right, where I will try to explicitly call out the time dependence. Right. So, now the charges and the electric fields can both be time varying quantities, right, but nevertheless the equation still holds. What do I mean by that? It's the equation as seen in the static form, right. So, the form of the equation doesn't seem to have changed just because the charges and the fields are now time varying, right. So, the Gauss's law for charges and magnetic fields remain the same, right. So, the form of both equations remain the same, the only difference being that these fields are now time dependent quantities. The last two equations, however, do change, right, change quite significantly. So, this surface integral B dot dA is what we called as the magnetic flux, right. So, which says that the line integral E dot ds over a closed contour is basically the negative of the time rate of change of magnetic flux through the surface enclosed by the contour. The negative sign came from the contribution from Dr. Lenz, and this is popularly known as the Faraday's law. And then lastly, we have the line integral for B, right. So, the last equation is popularly known as the Ampere-Maxwell equation, the last term being the contribution by Maxwell. I would say the entire set of 4 equations is actually called Maxwell's equations just from this simple addition. While it might look like a very simple one term that has been added, this really the power of this added term really gave us the full picture, right, of the interplay between electric and magnetic fields. And interestingly so, this contributing factor is one that seems to be missing in the derivations for your inductors and capacitors, right. So, keep that in mind. So, please remember that each of these fields are time dependent. Okay. So, the closed surface integral for E dot dA and B dot dA can be thought of as electric and magnetic fluxes, right. So, whenever there is a time rate of change of these fluxes, we see that the field of the other kind is being generated. Okay.